So yeah, hi everyone. We are here with Ron Pressler, leader of the project Loom in Java. So we're going to start our Q&A. So first, Ron, please introduce yourself.
Hi, buenos dias. My name is Ron Pressler. I'm based in London. I've been with Oracle for 4.5 years, and I work at the Oracle group that develops OpenJDK. It is called the Java Platform Group. We call it the JPG, and I'm the technical lead for Project Loom, which means that I'm in charge of the development. I'm not a manager, I'm a programmer, but I'm in charge of the technical aspects of Project Loom, defining what it does, how it does it, and how it does it. And I work, of course, with other people, including our architects, which you might know, people like Brian Getz and Mark Reinhold and John Rose. So they provide sort of a universal supervision, and then each project, like Loom, has its own subordinate lead, and I'm leading Project Loom.
How big is that team?
So the way projects work is that you submit a proposal. Once a project is accepted, a team is sort of naturally assembled. So the more senior programmers usually get to pick which project they can work on, and sometimes they work on multiple projects at once. So not everyone who works on Loom full time. Also, the number of people changes over time. For example, when we first started, we didn't have a dedicated member from the testing team, but now we do. We didn't have a dedicated member from the performance team, but now we do. People from the debugging team were added, etc. over time. But I would say that if you count just the people who work on Loom full time, right now it's about 8-9 people.
Okay, so yeah, let's start talking about Project Loom. So what is the best way to describe that project for you?
Okay, so Loom, like all OpenJDK projects, tries to solve an actual business problem, right? So we don't start with something technical like, I don't know, what should the type system be? We start with an actual real problem that people have with their program, with their applications. So in the case of Project Loom, the problem is writing servers, writing application servers. So that is, of course, sorry, I'm going to turn off Slack.
Don't worry.
When people, obviously servers are one of the biggest uses of Java, and I assume that most of you who work in Java work on developing servers. And the problem is that servers need to, are very concurrent applications. They need to respond and handle, they need to respond to and handle many requests that are mostly independent, and they come in at different times from multiple sources. And when Java started, there was a very simple way to do this, right? You would, back then we had, well, today too, but we had we had servlets, which then became JAX RS, more popular now. And you'd write very, very simple code. Mostly the way it would work is that every request that would hit your server would translate into a task that would execute start to finish on some thread. And that is basically the server model, and we call it a servlet model, and we call it the thread per request model. So every request runs start to finish on a thread. It might split up, it might use other concurrent tasks, but the core of the request starts on one thread and ends on that thread. That means that while a request is being processed, it is hanging on to a thread. And if a request takes, say, 100 milliseconds, just to throw out a number, usually it's less, but say 100 milliseconds, that means that for 100 milliseconds, one of your threads is occupied performing that request. And the problem is that as your throughput grows, you get more and more requests per second. If each of those requests takes still 100 milliseconds, in order to keep up with a higher throughput, you need to have more of those requests concurrently. And if each of them hangs on to a thread for 100 milliseconds, if it turns out you need 1,000 requests concurrently, you'll be consuming 1,000 threads. And the problem is that threads in Java are implemented as very thin wrappers around OS threads. So every Java thread is basically implemented as an OS thread. And the OS cannot support a sufficient number of threads in many cases. So if you have 1,000 concurrent requests, and each of those requests, say, wants to contact 10 other microservices. So today we have lots of microservices. So each of those requests wants to contact 10 other microservices in parallel. You'd see that you need, so that's 1,000 plus 10,000, that's 11,000 threads. And the OS just can't handle 11,000 threads. Even though what most of those threads do most of the time is just wait for I/O. So your server would become exhausted. You'd reach the limit long before you run out of CPU. And the reason for that is that in order to have a high throughput server applications, you need to handle many requests concurrently. And if each request means a thread, you need many threads. So the number of threads the OS can support becomes a bottleneck. So the business problem is, if people write such simple Java code, their servers become overloaded while they still have a lot of hardware to spare. You'd see that you can't handle any more requests, but you're only consuming 10% of the CPU. So that means that people waste money on buying more hardware that they don't actually need. The other side of this problem is that because the problem is so bad, some people said, you know what, let's not use the thread per request model. Instead of handling a request start to finish on a single thread, like I said, most of the time, what it's going to do is wait for I/O from the microservices. So they use asynchronous code, something like completable future or reactive. And the way that works is that the request handling doesn't run on a thread start to finish. It performs some calculation on a thread, and when it waits for I/O, it basically returns the thread to the pool to be used by some other task. And when the I/O operation completes, there's a handler being called, and it can continue. And this solves the scalability problem, because then you can have many requests. You can have many more requests than threads because a request doesn't hold on to a thread. But this comes at a very high price. That kind of code has several problems. First, you need to use completely different APIs, right? Instead of using simple java.net.sockets, you have to use the non-blocking Java NIO APIs or Netty or all that, which is first of all separate from, so you need to change the APIs you use. Second, writing that code is for some people not very pleasant, but most importantly, the platform, the Java runtime doesn't know anything about those small tasks. So if you try to debug them in the debugger, you can't step through them. The debugger knows to step through a thread. It doesn't know to step through an asynchronous pipeline. So you can't debug them. You can't profile them. A profiler knows to group operations by thread. Somebody said that one of their problems is that they write asynchronous code. They know their server is very busy doing I/O, and they run a profiler, and all they see is idle threads because there are some asynchronous I/O operations in the background, but the profiler doesn't know about them. So the Java runtime only knows threads. It doesn't know anything about those asynchronous pipelines. And if you get an exception, for example, like those of you who've tried to write asynchronous code know that if you get an exception, the stack trace is completely meaningless. Every piece of the pipeline is independent. You don't know who called you. The frame that called you is a part of the framework. It's not your own code. You don't have any context. So on the one hand, we have people who use the good thread per request model, which is very easy, but then they waste money on buying hardware they don't need because the server is exhausted after they're using 10% of the CPU. The other people say, okay, we want to use our full hardware, and they write asynchronous code, but then they have to waste much more money on development time, debugging, profiling, all that becomes much harder. So that is a problem. The solution, in retrospect, sounds simple. Just don't make threads so expensive. If the problem is that you can't have more than, say, 1,000 active threads, let's solve that. Let's have more than 1,000 threads. But the OS can't have more than 1,000 threads for, well, active threads. It can't do it sufficiently for various reasons. If people would want to know more, I can get into that. But the Java runtime can. The Java runtime can implement threads that are not OS threads. They're much, much cheaper. And we call them virtual threads. So Loom introduces virtual threads, and virtual threads behave just like today's Java threads. They implement the Java lang thread API. And the only difference is that you can start 1 million virtual threads, no problem. And once you have many threads, you can go back to the simple thread per request model. You can write very, very simple blocking code that scales just as well as asynchronous code. And it's not just that the code is simpler. Because virtual threads are threads, you can step through them in the debugger. You can use a profiler. The profiler does know about virtual threads because they're threads. You get meaningful stack traces. You can use thread locals. So Loom solves the problem of the dilemma between wasting money on hardware or wasting money on developers, and says, okay, you can win in both. Write simple code that's, I like to use the word harmonious with the platform and all its tools, while still get the same scalability. And I want to show you just one slide that perhaps will make this this was a slide from an internal presentation. So I had to present Loom to people inside Oracle. So I just want to show you one slide. Yeah. So here we took the Jetty server.
Wow.
We simulated a request that takes 100 milliseconds. So every request takes 100 milliseconds. And then we wanted to see how much load, how many requests per second it can handle. So if you just, so Jetty out of the box gives you 200, a pool of 200 threads, which now that we have, Loom gives us virtual threads. So what do we call the old threads? We decided to call them platform threads. So Jetty gives you 200 platform threads. So you start raising the number of requests, but when you hit 2000, which is no surprise because it's exactly 2000 times 1/10 of a second, which is equal to 200, which is the number of threads. So so beyond 2000, you don't have enough threads. So what happens is that your server becomes non-responsive. So this is it for your server, even though you're only using 2% of the CPU. So you'd say, okay, no problem.
Wow.
I'll just tell Jetty to use more platform threads. So you set it up to 800. So in that case, you get stuck with 8,000 concurrent requests. And that is when the server dies at 10% CPU. So you're using only 1/10 of your hardware and you're done. Now, of course, you could say, okay, let's have 1,000, but beyond 1,000 things, the OS just can't handle them. With virtual threads, you don't have a thread pool. Forget about a thread pool. Every incoming request, you do like sort of a new thread, you give it a brand new thread, and this is the green line here is with virtual threads. This is latency. So latency is 100 milliseconds. We go up to more than 20,000 requests per second. This is eventually some resource will get exhausted. So you will see the same thing when there is no limit on threads, but there is a limit on CPU. Eventually the CPU would run out, but we weren't able with our small setup, we just did it for a demo, to generate enough load to reach that point. So this is what Loom gives you.
Okay, so virtual threads is not a replacement for threads. It's just another implementation of threads, right?
Yes, it is not. It does not replace today's platform thread. When you create a thread with Loom, you decide whether you want it to be a platform thread that is tied to an OS thread or one of those lightweight virtual threads. And one thing that people sometimes misunderstand, and it's very important to explain, virtual threads are not faster threads. They don't do anything faster. They're not slower either, but they don't run your code faster. The difference is that you can have many of them. And for servers, if you have many more threads, that means that the server can handle more requests per second, a higher throughput. So we solve the problem of getting the full throughput that your hardware can support while keeping your simple code that works with all the tools.
Yeah, nice. And so besides that, there is anything like a disadvantage of using virtual threads, or what kind of tasks are better done with platform threads after virtual threads are introduced?
Right. So first, let me say that because virtual threads are Java threads, it doesn't cost you much. I mean, it's not like you have to think much in advance. You say, I will answer your question, but if you pick wrong, and then you say, oh, you know what, instead of a platform thread, I want a virtual thread, or vice versa. Instead of a virtual thread, I want a platform thread. Switching between them doesn't require changing your code. It's just when you create the thread, you pick, you want one or the other. So just try it with this one, try it with that one. So it's not like you have to think hard in advance. And with asynchronous code, that's a big problem. You have to say, I want to start with a simple thread per request model. I don't know if it's enough to handle my load, but if it's not, I have to rewrite my entire application in the asynchronous state. Here, you get it wrong, you just change how you create the thread. But to answer your question, first, the choice is very simple. The main difference between virtual threads and platform threads is that you can have many virtual threads, but not many platform threads. So if you want to run more than, say, 1,000 things concurrently, obviously you can only choose virtual threads. You can't use platform threads. So if you have, if you need to do many things concurrently, just use virtual threads. You don't have any other choice. If you only want to do a few things concurrently, then it probably doesn't matter much. However, like I said, eventually you're going to run out of CPU, and that there's not much we can do about it. So virtual threads help more when the code that runs on them is not particularly CPU bound. So if they spend a considerable amount of their time waiting for a message, waiting for IO, if all your thread does is, I don't know, machine learning, inverting a huge matrix for an hour, then virtual threads are not going to help. The number of computations you can do concurrently is equal to the number of CPU cores that you have. If you have 10 cores, you can run 10 computations concurrently. That's it. So any number of threads beyond that won't help. But of course, you can wait on many things concurrently, many more than a CPU. So if your code spends a significant amount of time waiting on a lock, on IO, on a queue, then having more threads will help increase the throughput, even though you don't have more CPUs.
Okay, yeah, Armando Alanis asked, is this going to have a huge impact on application servers performance? So if I understood you, it's not that they are going to make tasks faster, but they will handle more requests. So that's the impact that you're expecting on performance, right?
Precisely. It won't lower the latency of each request. The latency of the request is probably dominated, I don't know, by your database or your network. So it's not going to shorten the time it takes to handle each request, but it will let you work on more requests concurrently. So your server will have higher throughput. If today you're using the thread per request model, if you're using the asynchronous model, it will give you the same throughput as you do today, only with simpler code. Yeah.
Carlos Ricardo asks us, we can use mutex or another log mechanism with these new virtual threads, and I think you have touched that. It's just another kind of thread. So everything that is working with platform threads will work with virtual threads, including tools like the debugger and profilers,
yes.
Right?
Yes, but there is a small nuance here. It's very small, and because it was asked, I will respond to it, but I wouldn't spend too much time thinking about it. All the blocking IO operations work correctly. All the Java util concurrent locks, blocking queues, all that works the same way, but at a larger scale. Native monitors, which is what we call synchronized methods or synchronized blocks, work the same way on virtual threads, but they don't scale that way. They actually do block the underlying OS thread. So if you use if all you use synchronized for is very short in-memory operations, for example, it's used internally by hashmap, that is perfectly fine. But if you are doing very frequent and long-lived IO operations inside synchronized blocks or synchronized methods, you might want to consider switching those particular synchronized blocks with Java util concurrent reentrant lock. You can just try. So at first, don't do anything. Do you know? I don't know how many people here know JFR. So JFR is JDK flight recorder. It's like the next generation profiler that's built into the JDK. It's sort of a high performance log. If you have a problem there, JFR will emit events. Those events are called pinned threads. The virtual thread becomes stuck to the OS thread and it can't release it while you're inside a synchronized block. So it will tell you if that happens for too long, and then you can solve it. So it's not like you need to go now and change all of your uses of synchronized to Java to concurrent reentrant lock. But if you have places where you already know that you do a lot of I/O inside synchronized, you might want to think about changing that to reentrant lock.
Okay, nice. Ricardo also asked if these virtual threads require a specific hardware, and I guess kind of to that point, is there a hardware that better uses virtual threads, or that's just on the JVM side?
It's on the VM side. I don't. So I think the answer is no. But currently, Loom supports. So the platforms, the OpenJDK platforms that Oracle develops are x86 64-bit and ARM 64-bit. There are other companies that do ports to other platforms like PowerPC, etc. Those sometimes come later, but what I can say is that for all Intel machines and ARM 64 machines, Intel 64-bit and ARM 64-bit, they work just as well.
Okay. Yeah, Emir Cortez is asking probably one of those hot questions that you always get, when this will be available. And I know that it's hard to have like a release date, but do you have like kind of a roadmap of how are you going to deliver all these features and how close are you for having like a first preview of them?
We're close. Okay, so let's get this out of the way first. I believe we're very close, but the reason we don't say, well, part of the reason why we don't tell people when is because we don't want people to, make business decisions, and then, software often gets delayed, and then they say, you deceived us. And I once made that mistake. I made a prediction which turned out wrong, and people rightly made fun of me. So try not to do that again. But another problem is that oftentimes we don't know. We have started the process of integrating Loom, but so JDK 18 is coming out March, right? So JDK 18 is closed. We have a new version, a new feature release every 6 months. It is closed for new features 3 months in advance. So JDK 18 comes out in March. It means it was closed back in December. JDK 19 comes out in September, which means it will be closed in June. So in order to make JDK 19, we need to integrate by June. Such a large project, and such a large project takes a while to integrate. It needs to go through reviews. And so, and we can't do it in June because we don't want to put in these huge features at the end, right? We want to let them cook a bit. So we don't have much time to complete the integration process. So if we miss it, it's not going to be 19. So the answer is that I don't quite know. Things can go wrong. But in terms of process, I can't say more. Loom will first preview. So to those who don't know, preview features started out as being language features mostly, like records, and we had text blocks and switch expressions. So when we introduce a new language feature, it is first marked as preview, and then after 2 previews, so namely a year, it becomes GA, general availability. So what does preview mean? Practically, first of all, it means that in order to use a feature, you have to run both the JavaC compiler and the Java launcher, so the JVM instance, with the enable preview flag. And it also means, so you can choose to do it in production if you like to, but it also means that the feature is like, say, 95% done. And if you want to do that, you take it upon yourself the responsibility that maybe things will change, and you'll have to go back and change them. Once something is out of preview, then it's backward compatibility and for another decade or two. So virtual thread. So Project Loom consists of 3 features, and they are going to be introduced as 3 JEPs. So every big feature gets something called a JEP, a Java or JDK enhancement proposal. The main JEP is virtual threads, and that is going to go in as preview. 2 other JEPs are structured concurrency and scope locals. Scope locals are a sort of a lightweight and faster, more correct flavor of thread locals. And structured concurrency, and I can talk more about it if people ask. I think it's very interesting. Structured concurrency, because with Loom you can have so many threads, we wanted to help people write correct concurrent code easier and observe it in thread dumps more easily, etc. And that is structured concurrency. So those 2 features, which are much smaller, are not as mature as virtual threads. Virtual threads changes the API, the Java API, very, very little. Essentially, all it does, it adds one method to thread called isVirtual, and a new thread builder to construct either platform threads or virtual threads. It hardly changes the API, but those 2 features add new 2 APIs, and they're not as mature. So they're going to go in probably in the same release as virtual thread, but under what we call an incubation status. Incubation status is sort of lower than preview. It means that, so preview means that it is almost certain that within a year it will be done. With incubation, we don't give this promise, so it might be more, but it might be less, right? We don't. You can go directly from incubation to GA. You don't have to preview in between, but it means that with preview, you're saying, I don't expect any major changes. There might be small ones, not any major ones. With incubating features, there might be bigger changes. So those 2 features will go in as incubating features.
Nice. So yeah, Alberto Patiño was asking about writing concurrent code is hard. So the goal of a structured concurrency is that have like an API that is simple to use, right?
Yes, and let me again go to the slides. I do have some slides about this from the same internal presentation. Find it. Yeah, okay. So first of all, let me give credit. Structured concurrency, let me find it. Structured concurrency is a relatively new idea. It is spreading like wildfire in many languages. So Kotlin uses it, Rust wants to use it, C++ wants to use it, Python is using it. Actually, C was kind of the first, not internally. So it is relatively new, but it's not our idea. I'm looking for, let me post a link. So this was a blog post. So the terminology for structured concurrency was coined by someone called Sustrick, forget his first name, but it was popularized and made famous in this in this blog post I'm now posting in the chat, written by Nathaniel J. Smith. And this was one of the rare cases in my career when I read a blog post and I said, obviously, this is how we should do things. Like, how come we didn't think about this earlier? Like, this is it. But part of the reason why, while it's also still we want to do it in incubation, is that in Java, and I know some people don't like it, but we do it intentionally. We like adding features after everyone else. We like being late because many good ideas look like good ideas. For example, async await looks like a good idea. It turned out to be a horrible idea. And C# is paying the price for it. There's not much they could do about it, but we were happy to have waited. But so even if something looks great to us, we'd rather wait. But this looked so great that we said, and it's not very intrusive. It's just sort of an API on the side. So you know what? Let's incubate this and see how people like it. So let me show you what it is. I love it. I think so. Structured concurrency, or the name, is similar to structured programming. And what do we mean when we say structure or structured programming? We mean that the behavior of the program, the control flow, how instructions go from one to the other, how they jump back and forth, how they split, etc. The control flow of the program is reflected in the structure of the code, in the blocks of the code. So in structured programming, if people, I don't know how many people here, so I started programming BASIC in the 80s, right? But BASIC wasn't structured. We just had these go-tos. But today, you have methods, you have if statements, you have while loops. You see those curly braces. You say, okay, the block starts here, ends there. The loops, you can see the flow of the code with your eyes. That's structured. So structured concurrency. So how did structured programming come about? People wrote unstructured code with GoTo, and it turned out to be very hard to do. And over time, they came up with like best practices. For example, only jump backwards, never forwards. Don't jump into one place, into one instruction from two places, various stuff like that. And then after a while, they took those recommendations and baked them into the language. And that is structured programming that we know and love. And structured concurrency tries to do the same for concurrent code. So what structured programming does for sequential code, structured concurrency does for structured code. Now, I want you to pay attention to this very short and simple example here. And it is structured programming has become such a second nature to us, so obvious to us, that we fail to notice how much work it actually does. Not only, so in this case, the only structure we have is breaking the program into subroutines. Right, very simple, right? We didn't quite have this in BASIC. It was, well, a little bit different. So this is what we have here. It doesn't just make the code easier for us to read and understand. Okay, so there's a piece in foo, a piece in bar, a piece in baz. It also lets the runtime understand what we're doing. What do I mean by that? So here we have a method called foo. And it wants to do two operations, bar and baz. And let's say that what bar and baz do, they go out to some microservice and they return results. So they do some IO and return, and they might fail. And so it does both of those operations. It merges their results somehow and returns it. If one of them fails, say bar fails, it will throw an exception. And automatically, right, again, it's like, well, it's so obvious to us, but automatically, the Java runtime, if bar throws an exception, in this case, it will abort foo as well. Because bar is a part of foo, and if bar throws an exception, it propagates through foo, unless we catch it. But that's not everything. If we do a thread dump, what will we see? the thread that runs foo, we will see bar or baz on the stack right above foo. We know, the runtime knows that bar is working for foo. It knows that baz is working for foo. And we see that in the stack trace. Okay, but then we look at this code and we say, you know what? To call baz, I don't need the result of bar. And these two are very lengthy IO computations, operations. They go to 2 microservices. Let's do them concurrently. Okay, so you write this code. This code is correct. This code is correct. What do? We have some thread pool. We submit a call to a task that calls bar. We submit a task that calls baz. We get back futures. And then we wait in those futures. And we're careful, right? We need to be very careful, but this is good code. Any of them might have failed. So when we wait for them, we might get an exception. And if so, it gets propagated, fine. But what does foo want to do? If bar or baz fail, foo also fails, right? If one of them fails, foo will throw an exception. That's what we want in this case. We want both of them to succeed. But if one of them fails, we'll still keep waiting for the other one. The other one, or if we don't keep waiting, it will go on running. We don't count, it's not cancelled. It's still running in the background. Another problem is that if we do a stack trace, if we get to thread dump, what will we see? We will see 3 different threads. One thread will have a foo on the stack. It's going to be suck here and the call to get. One thread will have baz on the stack. One thread will have bar in the stack. And we won't be able to see that bar is working on for foo. We won't be able to see that baz is working for foo. So everything we know about the program is completely lost to the runtime. And finally, so what does structured concurrency do? It gets us back the same thing that structured programming gets for sequential code, but for concurrent code. So this is our current API for structured concurrency. And the rule for structured concurrency is very simple. Every time, so you start in foo, you split into multiple, into concurrent streams. So structured concurrency says, if you split into multiple streams, they must join back in the same code block. And the thing that does it is this try the resources block. So every task we spawn inside this structured task scope is guaranteed to have finished by the time we exit. That's a guarantee. Over here on this line, bar and baz are no longer running. We know that. This is an invariant that's enforced by this. And then we do something similar to before. We submit bar and baz, we call that fork. We get back futures, and then we call join. So this waits for them. But, so this waits for them. And then, okay, and then we choose this thing. We want to say that if one of them fails, cancel the other one. And this is specified here, shut down on failure. Sometimes we want to say shut down on success. So sometimes we might try to connect to multiple servers and we care about the first one that succeeds. So if one of them succeeds, we want to cancel the other one. Here we want, if one of them fails, we want to cancel the other ones. And of course, you can write your own policies and do it whichever way you like, more complex. But so if bar fails or baz fails, the other one will automatically be cancelled. But also there are exceptions. The first exception to be thrown will be centrally caught. And if we do this, throw if failed, this will propagate it. If we forget to do it, don't worry, nothing bad can happen. We then don't need to wait for the results because we've already waited them. If you want, you can call get, but we've added this new method result now. We know it's finished, so we know it's there, we can call result now. So this automatically cancels the other one. It makes sure that you propagate the error. You won't be able to, you'll see, you can try. You won't be able to do this without propagating the error. And the cool thing is that we have a new kind of thread dump, a structured thread dump that will show it will give you the bar stack trace. So bar is, each of those will be running in its own virtual thread. Bar has its own thread, baz has its own thread, and it will show you that those two threads are children of the thread running foo. The way we do it is that the thread dump is going to be in JSON, and the tools can turn this JSON into some graphical representation. And this makes sure you, number one, that it makes it easier to write concurrent code correctly. Number two, it makes it very easy to observe with thread dumps what is going on here, because the runtime now knows that bar and baz are working on behalf of foo. And this will happen only if you choose to use this structured task scope. You don't have to, but if you use it, then the runtime knows what you're doing.
That looks pretty cool, actually. So yeah, very intrigued by that. I guess, yeah, one of the other questions that I have seen people ask you a lot, and Alberto Patiño did that, is how this compares to other languages. So, and the first one that people mention is Go. So yeah. Is there a similar, okay, yeah, go ahead.
Yes, yes. Yes, and first, there are certainly big similarities. Virtual threads are a kind of what we call user mode threads. So they're threads that are not implemented in the operating system kernel. Everything that runs on your computer that is not the operating system runs in what's known as user mode. So those threads are implemented in user mode. So virtual threads are user mode threads. Go routines are user mode threads. Another example is Erlang. Erlang has these processes, those actors, they call them processes, and those are also user mode threads. So in that regard, virtual threads are very, very similar to Go routines in Go and processes in Erlang. There are, however, a few API differences. So in Go, you don't have a reference to a thread, to a Go routine. So in Java, we have a thread object. In Go, we don't have a Go routine object. The only way we can communicate with a Go routine is through channels. And that can be problematic because people who write Go programs sometimes have these Go routines that are left behind in the background. They sort of forget about them. And you can't hang on to them because you don't have any reference to them. They're just independent. So with Java, so Java's user mode threads, the virtual threads, implement the Java Lang thread API. So you have a reference to them, you can interrupt them, and that is one of the reasons why it's much, much easier to implement structured concurrency in Java. Go has an attempt to do it, but it's very hard for them to do. You can't cancel, you can't interrupt a Go routine in Go. There is no general mechanism for interruption. You have to set up a particular, for every Go routine, you need a special, has its own protocol of channel communication. In Java, we have a standard protocol, which is calling the thread interrupt method. And that is why it's much easier for us to do structured concurrency. But in terms of how they're used, how they're implemented, their general usefulness, virtual threads are absolutely very much like Go routines.
Nice. So yeah, another question that I have for you is, what is like the biggest misconception that you have seen when people talk about Loom that you will like to clarify today?
Oh, wow. Terrific question. I don't know if there's just one. Yeah, so first one I mentioned, some people tend to think that virtual threads are better or faster in some way. They're not. They are much faster to start. Starting a platform thread takes, I don't know, several microseconds. Starting a virtual thread takes nanoseconds. But they don't run your code faster. The main difference is that you can have many virtual threads. Another problem, I wouldn't say it's a misconception, but sort of a mistake I see when people started trying to experiment with Loom. And a common mistake is that they think they have some number of platform threads. So they go to their application, see where platform threads are created. Usually it's in some thread pool, and they replace, okay, instead of a platform thread, give me a virtual thread. That doesn't help at all, because virtual threads are not platform threads. So if you replace 100 platform threads that you have today with 100 virtual threads that you have today, you won't see any benefit. You are replacing your pool of 100 platform threads with 1 million virtual threads. How do you do that? You forget about your thread pool. You don't have thread pools. What you do have is, for every task today, in the example I showed you called submit to some thread pool, you create a new virtual thread for it. Now you might think, wait, I need to do a new thread. No, there is actually, and this I can show you. So first, let me do this. Let me show you where I find it. So you can go for yourself. I see Juan is wants to ask a question, but 1 minute. Okay, so first, where is that window? Ooh. Wait, can't find my window now. Too many open windows. Let's close this one. Just trying to show my browser. This, let me share. Ah, there we go. Okay, so first of all, you can go to jdk.java.net, and here you can download. So Loom is not yet in the JDK, but you can download an early access JDK with Loom in it here. So you go here, and you can download a JDK that has Loom. It also has JavaDoc. So let's go to the JavaDoc. And if you go, so first of all, let's see how you can create a virtual thread, but first, let's go to thread. One way to create a virtual thread, you see there's a new section here, virtual threads. One way to create a virtual thread is, that is actually not here, start virtual, yeah. It's just calling this method, thread.start virtual thread with a task. That's if you want to do something very simple. Another thing you can do is that we have this new thread builder API. And thread builder can create either virtual threads or platform threads. And I think we have an example here. Yeah. So to create a platform thread, you can do thread of platform, give it a name, etc. So thread of platform will give you a platform thread, or you could do a thread of virtual. It can also get a factory of virtual threads. I have to show you this, but most of the time you won't be using this, just because if you look in your code today, you hardly ever call new thread. Most of the time you use some thread pool, and you will continue not using this. What you will use instead is, let's go to executors. So this is what most of you should do at least. You might have this, you call executors new. What do you use? New cached. This is a common one. New cache thread pool. Okay. You call new cache thread pool. You get back an executor service, and then you submit tasks to it. And this new cache thread pool starts the threads for you. All you need to do is to call this new thing. We have a new thread per task executor, or a more easily in the part of the thread factory that creates virtual threads, or as a shortcut, new virtual thread per task executor. This gives you back an executor service. It is not a pool. Every task you submit to it, so it's the same executor service that you use today. You just execute or submit the APIs you already know. But for every task, you will automatically get a new virtual thread. So most of the time, either the framework will create a thread for you, or you will be using this, or you will be using this new structured concurrency thing. So back into the question, one mistake is people think, oh, I'll replace one for one. Instead of one virtual thread, I get one platform thread, I get the virtual thread. No, you replace your tasks with virtual threads. Every task gets a new virtual thread, and you don't need to construct virtual threads directly. You use this. I think those are the two main things that people mistake.
Okay, so yeah, Juan, can you give your question?
Yeah, sure. Can you hear me?
Yes.
Yeah.
Yeah, well, my question is about the reactive frameworks because most of the developers use reactive frameworks like Spring Webflux or Vertex or something like that, just to have a better management of the threads. But now with Project Log, do you think that this will replace these reactive frameworks that Java have? Or what do you think about that?
Let me say this. So this is a contentious issue because some people really like reactive frameworks. If you absolutely love what reactive frameworks do for you today, no one is taking them away, right? Everything stays, nothing is taken away. You can continue using them. But with virtual threads, you can get the same scalability as you do with reactive frameworks, using simple thread per request code with the same API with blocking IO. So you'll be able to get the full throughput of your machine. You'll be able to choose, do I want to use reactive or do I want to use simple thread per request with the blocking API? And they'll both give you the same sort of scalability or performance. So whichever one of those you prefer. I think that more people would prefer writing simple blocking code, but if you like writing asynchronous code, you're more than welcome to continue using it.
Yeah, I think that's, as you say, I have seen a lot of people that said like, this is not going to replace reactive programming. And I wonder if it's a case of people feeling familiar with something instead of something that is simpler to our models.
We'll find out. We'll find out. We'll see.
Yeah. Emir Cortez was also asking about if you know like application servers, like once this is available in general availability, how soon will those application servers start using the framework, the changes?
I think the answer is as soon as they start seeing benefits, and we will have, when Loom previews, I expect us, I mean, there are people working on it, to have a sort of a demo web server that would show them what kind of scalability they can get with simple blocking code. JAX-RS, simple, all the familiar Jakarta EE, all that, they'll be able to see. And if they're impressed, and I expect they will be, they will very quickly want to have those capabilities for them. So I think they're saying, okay, we'll wait and see. It's very easy. It's so easy to write code for Loom, even a server, that it's not going to take long for them.
But do you know if they are starting to do some tests and giving you feedback?
So some people definitely are. I know that. So inside Oracle, we have the Helidon. They're not part of the Java team, but they're in the same company. We have the Helidon team. So the Helidon team are absolutely experimenting with Loom, and also the Oracle JDBC team. Right, they want to make sure that the JDBC driver will work well, and you can do blocking calls for JDBC driver. Other than that, I don't know if I have seen some people experiment with Spring. I don't know if the people behind it specifically have started. At least they haven't told us. I remembered one thing I'd like to say. I wouldn't call it a misconception, but it's a question that often comes up and nobody asked it yet. I said right at the beginning that you never ever pool virtual threads. Now, pooling anything is done because it's expensive, right? So you want to share it. Virtual threads are not expensive, so there's no reason to pool them. But virtual threads perform another task, which is sort of accidental. If you have a pool of 100 threads, you know that at most it can do 100 things concurrently. So what people do today, they say, oh, I have this microservice and I know it could only handle up to 20 concurrent connections. So what I'll do is I'll start a, so when I run a method that says, I don't know, query that microservice, it will create a task, submit it to a dedicated thread pool representing that resource, that microservice that has 20 threads in it, and they'll submit it to that queue, and then they're guaranteed that no more than 20 calls to that microservices are active. And then they ask, okay, so how do we might still want to pool virtual threads for that. The answer is absolutely no. Do not do that. I mean, you could, that would be a bad idea. The reason it's a bad idea is because pools have some downsides. Once different tasks share the same thread, even at different times, they could accidentally leak thread locals from one to another. There are some safety issues and security issues there that if you can, if you don't have to pool, then don't pool. And so that's the problem with pooling, but you shouldn't do it because there's a much better way, with virtual threads at least. And the much better way is that there are constructs in the JDK designed specifically for that purpose, limiting concurrency. You want something to happen only 20 instances of it once. Thread pools are created to share something costly, but accidentally also do this. We do have in the JDK something that does this specifically, and that thing is a semaphore. So inside that method, where today you say, okay, that method calls the microservice, and I'm submitting a task to that thread pool with 20 threads. Instead, replace that in that method with a semaphore initialized to 20. And every time at the beginning of the method, you acquire the semaphore. At the end of the method, you release the semaphore. And that means that only 20 concurrent invocation of that method can happen. All the other ones will wait on that semaphore and will queue on that semaphore exactly as they would on that thread pool, without having to share the thread. So you get exactly what you want with a thread pool, but without the downsides and with a much more appropriate construct.
Nice. So yeah, I just have four rapid questions and we will end. So what is your favorite IDE?
What is my favorite IDE? I don't know about, I'm not so attached to IDEs. Currently, I write most of the code in C++. Several years ago, I started using VS Code for C++. I write very little Java, so most of the time, mostly tests, I write in VS Code. But sometimes when I need to do longer things, I like NetBeans and IntelliJ to a lesser degree. So
favorite drink while you are coding?
What?
Favorite drink while you are coding?
Tea and beer. So I have both of them, some beer here and some tea here. Yeah.
Favorite programming language besides Java?
Oh. Fluent in, not that many, but no to some degree. C++, assembly, at the beginning, basic, closure. back in the day, Scala. I know Julia well, Zig, which is a new programming language. I think, but languages I'm familiar with, like wrote certain programs in, it's a much longer list. That includes Haskell and Scala, and Kotlin, and MATLAB. Actually, the list is quite long. I have to prepare for that. But I will say, I will tell you this though. Other than Java, my favorite Java platform language is Clojure. I love Clojure.
Tabs or spaces?
What?
Tabs or spaces?
I honestly don't care. I think my current ID is set for spaces. I think that's what we use.
Okay, that's all that I have for you, Ron. So yeah, thank you very much, you, the translator, and the audience. It was very fun.
Thank you very much. Yeah, I enjoyed it. So thank you very much.
Okay.